Hello, everyone. This is part one of the lecture to replace class on Monday, April 19th. The topic is balancing redox reactions. And within that topic, what we're doing first is learning how we can take a reaction that has been previously balanced in acidic solution. That means using H+ to balance the H's. And we'll now see how we can manipulate the balanced reaction, keep it balanced, but have it be balanced without any H+ showing up anywhere. Instead, we'll have hydroxide showing up, and that's called balancing the reaction in basic solution. So the steps are these. First, we balance our reaction the normal way. And when we get to the step where we balance the O's, we balance with water, then we balance the H's with H+. So we balance the normal way, don't change anything. Once you have a balanced reaction in what we call acidic solution, where there's extra H+, then what we do is we're going to write the water reaction, that is the water dissociation reaction, either forwards in the direction of water dissociating to make H+ and OH-, or we'll write it backwards to show H+ and OH- coming together to make water. And what we do is we write that reaction multiplied by some factor such that the H+'s cancel. There will be the same number of H+'s on opposite sides. And so here's an example of a reaction that, if I'm not mistaken, we balanced in class on Wednesday the 14th. I think we ended up with this situation, and you can see that on the left-hand side, we ended up with 4 H+. And so we would say, because there's H+ appearing in the balanced redox reaction, this is balanced in acidic solution. So in order to balance this thing in basic solution, what we do is we follow step 2, and we're going to bring an arrow down here right underneath the old arrow. And we're going to note that there's 4 H+. So we're going to write 4 H+ on the right. And then to go along with those 4 H+, we're going to write 4 OH- on the right, and we'll write the 4 waters that make them on the left. And now what we do is we draw a line, and we then cancel the H+. Now we then combine or cancel, or whatever it might be, any water molecules. Often there will be water molecules that will appear on opposite sides. Occasionally, like in this example, there's water molecules that appear on both sides. So now we'll bring down our final arrow, and we see 8 H2O. And on the right, we see the new 4 OH-. You can probably already see that I'm going to run out of space on the right, but I think you'll understand how this all goes. And now, since everything has been canceled and brought down to the new reaction line that we've modified, we can just bring all the rest of the pieces down exactly like they are in the balanced reaction. So we end up with 6ClO2- and 4NH4+ and 3Pb2+ on the right. Over here on the left, then we end with 3PbCl2 and 4HNO2. So now we should be able to verify that everything is still balanced. And if you look at all of our atoms, hope I can count these right, 4 H's there, 16 more there, that's 20 H's. I've got 4 H's right there. I've got 16 there, that's 20 H's, 4 N's, 4 N's, 8 O's there, and 8 more, 16 O's total, 4 there, and 12 makes 16. 3 leads, 3 leads, 6 chlorines, 6 chlorines. I think that accounts for all the atoms. And now we look at the left-hand side and we see 0 electrical charge, 0 and 0. So a total of 0 on the left. On the right, we better have 0. 4- and 6-, that makes 10-. And then we got +4, and we got +6, so that makes 0 total. So we have now a balanced reaction in basic solution. Those are the steps. And now from here on out, we're going to do balancing in acidic solution, and then also add in the same reaction, but balanced in basic solution. So our first reaction that we're going to study here is going to be shown at the top, unbalanced. So here we go. Whoops, that's not right. Here we go. NO3 minus CrOH3 Cr2O7 2 minus and N2O. So there's our unbalanced reaction. And following our steps, we've got to figure out what's being oxidized and what's being reduced. And I think most of you can quickly figure out that nitrogen here is +5. And nitrogen over here looks like it's +1. So there's our reduction. Chromium in chromium 3 hydroxide is +3. Chromium in dichromate, if you do all the math to figure out the oxidation state, you'll see that it's +6. So +3 to +6 is an oxidation. And there's our 2 half reactions, but unbalanced. So let's start with our oxidation reaction. So we have, let's see, CrOH3 going to make Cr2O7. Okay, first step is make sure that our redox atoms themselves are balanced. And so I'm seeing 2 chromiums and 1, put 2 there. Then we're going to see if there are any other extraneous atoms that aren't O or H, and there aren't any. Now we balance our O's. And so I see 7 O's on this side and 6 on this side. So that'll mean we need 1 on the left. Now we're going to count up all of our H's, and I see 2. And I see 6 more right there. So that's 8 H's. So I'll put 8 H's on the right. And now I'll count up my total electrical charge, 0 over here. Looks like I have -2 and +8 or +6. So I need 6 electrons. And so there is my oxidation reaction. Here's my reduction reaction, starting with NO3 minus and ending with N2O. So balance the redox atoms first. That's gives me 2 N's on both sides. Now look for extraneous atoms. I don't see any. Look for O. I have 6 O's and 1. So I need 5 waters. Count up all my hydrogens on both sides. I have 10 H's on this side and none. So I need 10 on this side. And now look at my electrical charges. And I've got 0 over here. -2 plus 10. I have +8 on this side. So I need 8 electrons. So there are my 2 reactions balanced in the half reaction situation. Now I need to look at the least common multiple of 6 and 8, and I think that looks like it's 24. So I'm going to have to multiply this top reaction by 3. And the bottom reaction I'm going to have to multiply, I'm sorry, I'm going to multiply the top reaction by 4. I got that in the wrong spot. And the bottom reaction I'm going to have to multiply it by 3. And that'll give me 24 electrons, and 4 times 6 is 24 electrons. So then rewriting both of those reactions, I end up with 4 H2O and 8 CrOH3 and 4 Cr2O7 2 minus and 32 H plus and 24 electrons. Okay, looking at the bottom reaction and multiplying it by its factor of 3, I've got 24 electrons, 30 H plus, 6 nitrates, got 3 N2Os, and then I have 15 waters. Okay, now I cancel and add, etc., to get both of those reactions added together. 24 electrons cancel. I'm looking for my waters here. 4 waters and 15 waters, that gives me 11 on the right. Then let's look at the H plus. I think we've got here 32 on the right and 30 on the left. That gives me 2 more. Uncanceled on the right. Let's see, now I think everything else, we just bring it down to the reaction line. 4 Cr2O7 2 minus and 3 N2O. And then over on the other side, we've got 8 CrOH3 3, and we've got 6 nitrates. So that should all be balanced in acidic solution, and now we're going to balance it in basic solution. So if the question on an exam says balance this in acidic solution, we're done. If the question on an exam says balance this in basic solution, we're almost there. We follow the steps to this point, and then we're going to add in the water reaction such that we cancel those 2 H pluses. So we look to see the 2 H pluses, and we put 2 on the left. Then we put 2 hydroxides on the left. And then we write the 2 waters that they would form together on the right. And now we do our canceling and adding, etc. And we cancel out our 2 H pluses, and we end up with, looks like 13 waters. And then we end up with our 2 hydroxides. And finally, we bring everything else down. And so we've got 4Cr2O7, 2 minus, and 3N2O. And on the other side, looks like we have 8CrOH3 and 6 nitrates. So there is the very same unbalanced reaction written in acidic balanced form and then in basic balanced form. Here's an interesting kind of reaction that is sort of like one we did in lab. So here's the unbalanced reaction, MnO4 minus. It's our only reactant, and it makes Mn in 2 different oxidation states. I'm sorry, this should be 2 minus. Okay, so we have something called manganate, if you really want to know. Manganese 4 dioxide, and then this is permanganate. So thinking about all the oxidation states, if you do this really quick, we've got +6 manganese here. We've got +4 manganese there. So +6 to +4, that looks to me like a reduction. But in the permanganate, manganese is in the +7 state. So you go from +6 to +7, that looks to me like an oxidation. So the name for this kind of reaction is called a disproportionation reaction. And in lab, we did a reverse disproportionation reaction with iodine. So the main issue is that you just have to follow the rules and don't do anything differently, and you'll be able to balance this one perfectly well. Here's how it goes. So we'll take our reduction reaction, let's say first, and we'll write that one. So we're going to balance our redox atoms first. They're balanced. Extraneous atoms, there aren't any. Balance O's. We're going to add 2 waters. And then we're going to balance our H pluses. So 4 H pluses are needed on the left. And then now we're going to count up our total charge, 0, -2, +4, +2 overall here. So we need 2 electrons. And there's our reduction balanced. Here's our oxidation balanced. So we're going to go the same. MnO4 2 minus ends up getting oxidized. So to MnO4 minus. And we balance our redox atoms, they're balanced. We balance our O's, they're balanced. We balance our H's, they're balanced. And we just have to balance the charge. We have a -2 and a -1. So we bring the high side, -1, down to the low side, -2, by adding an electron here. All right, that was kind of simple. So now we're going to take everything and add everything together and cancel what we can cancel. So I think the first thing, actually, I'm sorry, we have to do is we have to get the electrons to cancel. So we've got 2 on the left in the reduction, and we have 1 on the right. So we have to multiply everything here by 2. And now we can cancel our electrons. And then we can see that the waters actually don't cancel in this reaction, nor does the H plus. All right, we end up with 1 manganate plus 2 more manganates, so that makes 3. Okay, and so we bring down the stuff on the right, and we end up with MnO2 and 2MnO4 minus. And so now we should have a balanced reaction in acidic solution. And now to balance this thing in basic solution, we're just going to follow the same pattern we had in the last case. We look to see how many H pluses there are and on which side. So 4 H pluses on the left, put 4 on the right, put 4 hydroxides on the right, and 4 waters on the left. Add everything up and cancel. So the H pluses cancel. 2 waters and 4 waters give us 2 on the left, 4 OH minuses left on the right, and then we bring everything else down. Okay, that's how you balance a disproportionation reaction that involves either the same reaction or a reverse disproportionation reaction, which would involve the same product. Here's another one that illustrates another strange principle, and that is that we always have to remember that no matter what's going on in the redox reaction, H is always balanced with H plus, and O is always balanced with H2O. So our unbalanced reaction in this particular case looks like this. Well, maybe it looks like this. There you go. Now you can see it. Okay, so there's our unbalanced reaction. Thinking about all the oxidation states and figuring out the oxidation and the reduction. H is in the 0 oxidation state here in elemental hydrogen. Thinking about chlorate ion as -1, and there's 3 of them. That makes a total of -3. That means bismuth must be 3 plus. Chlorine within the chlorate ion, if you extract out the ClO3 minus and think about it, chlorine ends up as +5. All right. Over here on the right, then, we end up with hydrogen in the +1 state. So we can see that hydrogen's changing in its oxidation state from 0 to +1. We see oxygen here, -2, it's still -2. We see chlorine, however, is in the 0 oxidation state, whereas it had been in the +5 oxidation state in the chlorate ion. So there's our reduction. And then lastly, we see this extraneous ion, bismuth 3 plus, which was in the +3 state over here, and it's just present because it has to be present for balancing. And it doesn't change in its oxidation state. So anyways, as we can see then, the reaction involving hydrogen is our oxidation, and then involving chlorine is our reduction. So let's just do the hard one first. Let's do the hydrogen first. So H2, I'm not even going to write anything on the right because I know that we always balance H2 with H plus. And so even though it appears on the right in the form of water, I'm going to balance it with H plus. So I don't even go there. I write H plus. I need 2 of them. And then I can see the only thing that remains is 2 electrons. And that's how I'm going to balance my H in, even though it is appearing that H goes from 0 to +1 and ends up as water. We'll see what happens later. In the other reaction, we're going to do it, and it shouldn't seem any different than any of the other ones that we've ever done. So we're going to take our BiClO33, to chlorine, because it's chlorine that's undergoing the reduction. And I'm going to balance my redox atoms first. I've got 3 chlorines over here, and I've got 2 in this case. So I need least common multiple 6. So I'm going to go like this. Now I've got my chlorines balanced. Those are my redox atoms. Next thing I think about are extraneous atoms that aren't O or H, and I see that bismuth is one of those. So I've got 2 bismuths, and I need to bring down those bismuths from the unbalanced reaction as Bi3+, because that's how they're given to me. Now I can balance my oxygens, and so what I see here is 3 oxygens in a chlorate ion, but I have 3 chlorate ions, so that's 9, but I have 2 bismuth 3 chlorates, so that means I've got a grand total of, looks like 18 O's. And then I'm going to balance my H's, so 36 H's, none on the left. And then I'm ready for electrons, so +6 on the right, looks like +36 on the left, so 30 electrons. Okay, so I've got my 2 half reactions balanced. My least common multiple between 2 and 30 is 30, so I'll multiply this reaction by 15. And I'm just going to bring it right below here and multiply everything in there by 15. So I've got 15 H2s makes 30 H plus and 30 electrons. And now I can cancel. So looking at my electrons, they cancel. Looking at my H plus, I've got 30 on the right, 36 on the left, so 6. Looking at my waters, I only have water on the right, so 18 there. Let's see what's next. And I think everything else just comes down. So 3Cl2, 2Bi3+, and then 15H2, and then 2BiClO3, 3. There's my reaction balanced in acidic solution. And if we wanted to balance it in basic solution, we can see that 6H pluses are there. So 6H plus, 6OH minus, 6 waters. Okay, and then we bring everything else down. That's the way you play around with a reaction in which hydrogen is itself undergoing an oxidation or a reduction. We just remember that we just always balance it with H plus. All right, last example involves the same kind of thing, but where instead of thinking about hydrogen, we're thinking about oxygen. So here's our unbalanced reaction. K is +1 here. It's always +1, and it's +1 there. So it's not undergoing oxidation or reduction. N in NO2. This is part of the nitrite ion, so that's NO2 minus. And so nitrogen here is going to be +3. Oxygen's -2. Here oxygen is 0. And here nitrogen 0. So we can see that our nitrogen is going down, reduction. And we can see that our oxygen, going from -2 to 0, is going up. It's being oxidized. So let's just go right for the oxygen first. So we're going to start with KNO2. I'm sorry, in my notes here, I started doing the nitrogen first. We're going to do the nitrogen first. So we're going to do KNO2 to N2. All right, so then we balance our redox atoms first, balancing the N's. Then we're going to balance our extraneous atoms, potassium Now we're going to balance our O's. And now we're going to balance our H's. And now we finally balance our electrons. +2, +8, bring the high side down to the low side with 6 electrons. Okay, now finally, we're going to go back to our O in the order that I did it on my lecture notes here. So what we see is that we always balance O with water. And I see O on the left-hand side with the same oxidation state, -2, as it would have in water. And I see O on the right with the unusual oxidation state of 0. So I'm going to pick the one on the right and write it in there. And I'm going to balance that O with water. And it looks like I need 2 waters. Notice that I'm just completely neglecting the KNO2. Now I'm going to balance my H's. Balance my charge, 0 and +4 with 4 electrons. And now we can sum everything up. Looks like I've got my H pluses 4 on the left. Oh, I'm sorry, I forgot to do, never mind. I forgot to do my electrons. My least common multiple is 12, so I've got to multiply this reaction by 3. Never mind here, we'll multiply this reaction by 3 to get 12, and we'll multiply the top reaction by 2 to get 12, and then we should have something that we can actually then finally balance. So our first reaction is going to be 12 electrons plus 2 KNO2, whoops, 4. Let's see, is that right? Yes, 4 KNO2. And I don't want to forget about my 16 electron or 16 H plus. Then I'm going to make, what is it going to be? 2 N2s, and then 4 K plus. And then it looks like 8 waters. Let me check my own work just to make sure I'm following along and not making any more mistakes here. Okay, that looks good. Now I'm going to do this bottom reaction multiplied by 3, so I have 6 waters. Make 3 O2s, and 3 times 4 H pluses is 12 H pluses, and 12 electrons. Okay, now I can finally do what I started to do there, cancel my electrons, and then I can cancel my H pluses and waters and stuff. So I've got 16 H plus on the left and 12 on the right. That gives me 4. 6 waters on the left, 8 waters on the right. That gives me 2. Then I think everything else can be just simply brought down. So on the left, I just have left 4 KNO2s. And on the right, I've got my 3 O2, 2 N2, and 4 K plus. Let me check to see that I did all of this right. Okay, and if we want to balance this in acidic, I'm sorry, this is balanced in acidic. We want to balance it in basic solution. Put the same number of H pluses on the other side of the arrow. That same number of hydroxides. That same number of waters. Cancel. Now bring everything else down. And that's how you do all sorts of different kinds of balancing of redox reactions in both acidic and basic solution, and even involving when oxygen itself, or on one of the previous examples, when hydrogen itself is involved in the redox.